Hi, let us proceed with the examples related to the design of column. So far, we have done proposing the critical load arrangements for different columns in the key plane, depending on the layout of the key plane, as well as the columns that we are designing. The maximum load arrangements varies. A column may be subjected to uni-axial load and also biaxial load. The bending moment can be acting in the major axis or the minor axis. We will have to analyze the columns separately in order to determine that. Next, we have discussed about the maximum and the minimum UDL loads acting onto the structures. The calculated UDL loads for the ground floor, first floor, and the roof floors are obtained here. Now we will proceed with the next sub-questions, asking us to calculate the critical loads acting onto the ground floor column B3, referring to the key plane. This is column B3. Ground floor column B3 refers to this column. The critical load arrangements is indicated here, which we have calculated previously. In order to generate the maximum possible moment here, you will have the maximum load here. Since there is no beam here, there won't be any loading here. As for the roof floor, we will use the maximum loads throughout. To determine the critical loads, you need to determine the axial loads and the moment. The axial loads taken by this column, it will be everything above the columns. That will give you maximum load, and maximum loads here. As for the moment, there will be two moments, one at each end of the column. To determine the moments taken by the column, we will need to first get the stiffness of the column and then the total stiffness of all members at the joint. Whatever moment acting onto the joint here, which is as a result of the fixed moment caused by the UDL loads acting onto the beam here, this moment shall be shared among all the members connecting the joint. The amount of moment taken by each member is subjected to the stiffness of that particular member relative to the total stiffness of all members connecting the joint. Therefore, in order for you to get the moments at this end of the column, you will need to first get the fixed moments of the beam. Since you have no loads to counteract the moment shall be taken by all three members here. Get the stiffness of the column divided by total stiffness of all the members, multiply with the fixed moment, then you get the moment taken by the column at this end. You will have another moment here. You will do the same process, get the largest moment possible, which the critical load arrangements can be maximum here and minimum here, or maximum here and minimum here. Either way will do, since both span here are the same, 6 meters. Assuming we have the maximum load here and the minimum load here, you will have fixed moments due to both beams. The balance of the moment shall be taken by all the members connecting this joint here. Again, get the distribution factors of the column here, multiply with the moments to be taken by this joint, you will get the moments for this column. Having this understood, Let us look into the calculation steps. First, we will need to calculate the axial load. We are talking about this column, and it is meant to carry the loads all above the columns. For simplicity, we will assume the beams are all simply supported. Half of the loads of the beam will go here. Another half will go here. Same goes to this. To calculate the load, you get the UDL times the span divided by 2. We need to calculate the loads from the left hand side and the right hand side of the roof floor. As for the first floor, you only deal with the left hand side, since the right hand side you do not have any beam. Now, in terms of the UDL, we have calculated previously. The maximum UDL acting onto the roof floor, it will be 2.82 kN per meter. As for the maximum loads for the first floor, it will be 10.74 kN per meter. Having this written down, now you're going to calculate the loads from the left hand side and the right hand side of the columns. The UDL of the roof floor times the span divided by 2, you get the loads from the left hand side. You will do the same for the right hand side. And then for the first floor, the UDL multiply the span divided by 2, you get 32.2. You don't have any beam on the right hand side, therefore there will be 0 load. Your total axial loads, it will be the summations of all these vertical loads. 8.46 right hand side. In total, you will have 49.12 kN. Now that you have acquired the critical axial load, next you will need to determine the moment taken by the column at this end and also this end. In order to do so, you will need to first determine the moments to be taken by the two joints. Let us deal with this joint first. Get the fixed end moment for the beam here. Since you don't have a beam here, now the moment taken by this joint, it will be purely governed by this fixed end moment. We calculate the fixed end moment, assuming the beam is continuous throughout. The formula will be WL square per 12. W is 10.74 kN per meter, L 6 meters, WL square per 12, you get 32.2 kN meter. There is no moment from the other side. That means this fixed end moment shall be fully taken by the joint. Let us put this 32.22 kN meter on hold first. We're going to calculate the distribution factors and then get the moments taken by the column. We will first determine the moment taken by this joint before we proceed with the distribution factors. To get the largest moment possible for this joint, you will have the maximum UDL here and the minimum UDL here. The magnitude of the load, it will refer to the previous calculations. For ground floor, maximum load is 10.74. Minimum load, it will be 3.24. Use those UDLs to generate the fixed end moment. W L square per 12. You will do the same for the right hand side. W L square per 12. You will see differences in terms of the moment. It means that you will have moments from this side and also moment from this side. The two moments cancel out each other. The differences between the two moments here, it shall be the moments taken by the joint. That's why we calculate the differences between this 32 point something and 9 point something. Based on the calculated result, we know that this column, the top end will have the moment 32 point something, and the bottom end will have the moment 22 point something. These moments are not fully taken by the column. You will need to first calculate the distribution factors in order to determine the amount of moment taken by this column. To do so, you will require the stiffness. You need the stiffness of the column as well as the stiffness of the beam. The formula for the stiffness is K equals to EI per L. For simplicity, we will assume the E here equals to 1. This is because later during the computations of the distribution factors, the E shall cancel out each other. Even though you use the actual value of the E, it will still end up to be the same distribution factors. Now you will need to get the I and also the L. Let us first deal with the moment of inertia. Especially for the column, you will have to be careful with the moment of inertia. Look at the orientations of the column, and then look at the layout of the critical loop arrangement. There will be loops from this side, no loop from the other side. When the column is arranged in this manner, this will be the major axis and this will be the minor axis. Based on the locations of the loop, you know that the bending, it will be towards the major axis. When the bending is towards the major axis, that means the H will be the longer span of the column. The column size is given 300 times 150. That gives you 150 times 300. The H will be 300. Now in the case that the columns is arranged in the other orientation, under the critical loop arrangement, the bending is in these directions. That will give you bending in the minor axis. As a result, your H, it will be parallel to the directions of bending, whereas your B, it will be perpendicular to the directions of bending. If the orientations of the columns is in the other direction, your B and H shall swap. Coming back to this case here, the bending is in the major axis, then the H, it will be 0.3 meters. Calculate the moment of inertia, which is BH power of 3 divided by 12. B times H power of 3 divided by 12. Having the I obtained, we are looking into the effective length of the column. This you will need to refer to the elevations of the frame. To get the effective length of the column here, you will need to refer to the story height minus the beam height in order to get the clear span of the column. 4 meters minus 0.45 meters, which is the dimensions of the beam, you get 3.55 meters. This is how you get this 3.55. Let's say now you want to get the effective length of this column. Take the story height minus the height of the roof beam. You will get the clear span here, 3.05. You can do the same for the stub. 1.25 meters minus 0.45 meters, you get 0.8 meters. Now you can get the stiffness of the columns. Take the I divided by L, you get the stiffness of the column. And then you do the stiffness for the beam. The dimensions of the beams is given, which is equals to 150 times 450. The B, it will be 0.15 and the H, it will be 0.45. The effective length, it will be 6 meters as given by the key plate. Calculate the moment of inertia. B H power of 3 divided by 12, you get the moment of inertia. Find the stiffness. E I per L. E, we take it as 1 for simplicity. That gives us I divided by L, you get the stiffness here. I divided by L, you get another stiffness. From the elevations of the structure, you have beams on both sides at the roof level. For the first floor, you have only beams on the left hand side. And then coming back to the ground floor, you have beams on the both sides. That gives you the stiffness. No stiffness at the first floor on the right hand side. You can now transfer the stiffness into the diagram. This column will have the stiffness as indicated here. And then this column, the stiffness we have calculated here. As for the stiffness of the stump, we have calculated here. And then we bring in the stiffness of the beams. First floor stiffness, ground floor stiffness. And remember that for the stiffness of the beam, always multiply with 0.5. Why is it so? It is because of this setup. We are analyzing 1 point subframe where you will have half stiffness for the beam and full stiffness for the column. Analyzing this will get the moments acting onto the column. With that said, you can now calculate the distribution factors. The distribution factors, you will need to calculate the stiffness of the column divided by the total stiffness of that particular joint. Let us first deal with this end. There are 3 members here. You want to get the moment of this column. Take this column stiffness divided by the total stiffness of all members at the joint. That means this plus this plus this. You don't have any beam here, so you will assume 0 stiffness here. This calculation step is reflected by the equation here. Ultimately, you get the distribution factors 0.24 at this joint here. That means this column will take 24% of the total moments at the joint here. Then you do the same to get the distribution factors of the column here. Get this stiffness divided by the total stiffness of all the members at the joint, which means this plus this plus this plus this. You found that this column will take 13.5% of the moments acting onto the joint here. Now that you obtain the distribution factors, multiply the distribution factors with the moments acting onto the joint. The upper joint have the moment 32.22, multiply 0.24 distribution factors. The lower joint have the moment 22.5. multiply with 0.135, the distribution factors for the column. Ultimately, you will get these two moments here. To conclude this, you have calculated the critical load based on the critical load arrangement for this column. The total axial loads is 49.12, and the moments at both ends of the column, it will be 7.73 and 3.04. That gives you NED 49.12 kN, M2 7.73 and M1 3.04. Later, when you want to design for the column, you may use this value in order to determine the main reinforcement bar required in the column.